This is our first lecture in chapter 14. You can see the name. We're talking about chemical kinetics. And before getting into the material of the chapter, I just want to give a little overview of a couple of terms that chemists throw around. One is including kinetics. I want to try to make a distinction between a couple of fields in chemistry, and one is kinetics, dealing with this chapter, and really the other topic is the one that we deal with we deal with this one more than kinetics for this class, and it's thermodynamics. And in chapter, I should say, chapter 5, first Gen Chem, when we talked about thermodynamics, we talked about a term called enthalpy popped up, and we essentially, related that to the heat change of a particular reaction, and in some ways that's about as far as we went. How is the temperature going to change in a particular chemical reaction? Now, in a broader sense, thermodynamics will help predict whether a chemical reaction will occur, and the term that we use for that is a spontaneous reaction. So a broader sense of what thermodynamics is going to tell us is dealing with something that in some way it's more important than heat. Heat is a component of it for us, and it's this notion of whether a reaction is spontaneous or not. And what I mean by that is if we look at just a simple notion of a reaction, A going to B, the question in terms of spontaneity is spontaneous reaction doesn't mean that it forms instantaneously. Everything's converted over at once. Spontaneous means is that over time, and it doesn't really address how long it takes, that the B products are favored over A reactants is what spontaneous means. And that is in some ways more of what we study in this second semester. Kinetics, on the other hand, is this I guess I alluded to it a few seconds ago, in terms of if this A goes to B very quickly within a few seconds, if you had this huge amount of A going to B very quickly, then we say that it's very fast. We say it has a high rate. Is this rate phrase pops up a lot, and we're going to associate it with velocity. So this chapter 14 is the only one that we really dig deep into the kinetic issue, and so again, just because something happens very quickly doesn't necessarily mean that the products are favored to a great extent, if you will. There's a balancing act that takes place here that we'll look at in the next chapter, and that's more associated with this notion of thermodynamic spontaneity, and which are the products or the reactants favored under certain conditions, and then how quickly they reach that condition is a study of kinetics. And now this rate that I'm talking about of chemical reaction, a little chapter overview. Rate shows up all the way through this chapter, and pretty much there's 4 lectures to the series. The last 2 topics here I've just went ahead and combined. Catalysts, I'll define them, talk a little bit about them, but they're not for this class. They're not really. It's not a large enough topic to dedicate an entire lecture to. So this is the 4th one. I'm anticipating to be a little bit long. There's a lot of math through here. this initial one, there's a introduction to concepts and some math, but these two you'll want to. I would advise looking through the chapter, reading the chapter, at least skimming it somewhat before listening to the lectures here, just so you can get a little bit of an overview. And so let me in this first talk, let me talk about reaction rates and try to put a little finer edge in terms of what's referred to as an average rate and what's referred to as an instantaneous rate, and we'll get into that as we go through the talk. So like I've said before, the reaction rate tells us how fast the reaction is going to take place, and we have some notion of this this idea of things taking place quickly or slowly. Over time, a piece of paper is going to decompose if it's left out in the atmosphere, and that's a very slow process. It's a slow reaction rate. Whereas if you want to describe, let's pull something from the last chapter maybe. And let's say the water is at about, I don't know, I don't want to, let's say just 80 degrees Celsius is pretty hot. It's 20 degrees from boiling, so it's a very hot hot solvent, and you dump this solid in there, and it's quickly, it's going to proceed to the solution formation, well less than a minute, even if like a handful of salt into a bucket of hot water or something. That's a very fast rate, and so there's a lot of conditions that affect how fast the rate occurs, and you can see them here, and I'm going to use this example to illustrate the first three. Again, I'm not going to deal with catalysts until the last part of the talk. I'll probably define it here, but I'm not going to get into it. And these three, I'm actually going to talk about this particular reaction we see. This is in the book. What they have here is some steel wool, and it's, I don't know the exact combination of elements that come together to make steel wool. Iron is by far, I'd say, the majority component. And so notice what they're doing. And first, let me actually, if I was to redo these slides, I might actually put temperature first here, because, for example, if I had a wad of steel wool just lying around the house, it'll slowly oxidize. This is what's happening in the burner here. This is the basic reaction that's occurring. It's forming rust, is what it's doing. And being a chemist, I can't help it. I have to balance everything. And so there's our solid iron, oxygen gas, and then this is rust here. Now you don't see the rust in here because everything's hot and red, but that's essentially what's happening in the breakdown of the steel wool here. And again, if it's at ambient conditions, room temperature, and let's say the humidity in the air is normal, then this process, can occur over, I don't know, the course of months or years, and you'll mess up your Brillo pad that way. But then notice what happens once you put it in a burner. This burner central core of the burner here is over 1,000 degrees Celsius, and so that increase in temperature increases the oxidation process. Okay, and we can appreciate the temperature comment, I think, with the example of the salt water as well. Now, if the physical state here of the steel wool is very different than if you just had a block of iron metal sitting on the table. If you burn this, if you put this in a burner, it'll turn red, and I guess the outside will oxidize a bit, and maybe if it's hot enough it would melt, but I don't think you would get this rapid conversion over to this this increased oxidation rate that you see in the burner. And so partly it's due to the physical state of the substance up here. Here it's that finely spun wool, and it's got a lot of surface area, and it can react over a greater amount of the sample. The same thing up here. If I had a big rock of sodium chloride and put in water, that dissolves much more slowly than some granulated table salt that you find in your home. And so physical state can be have an effect on the reaction. And then this notion of concentration. So and the concentration is shown by considering both panels here. This is ambient conditions. I don't know, oxygen is around 22% of the atmosphere. And you can see, right, oxygen is one of the main components, the main reactants in this process. And then if you look at the figure caption in the book, this is atmosphere of pure O2. And what they're doing here is they're taking this hot, burning steel wool, and they're plunging it into a atmosphere of pure oxygen. There's a very, I don't even have to say anything. In some sense, there's a very rapid increase in the oxidation of the iron. And again, so just appreciate the three things here that can help a reaction go forward as we talk about the different reactions in this class. And we'll actually, in some sense, we'll come back to this in the next chapter, and how we can, if we increase the concentration on either one of these two, we tend to shift it to this side. Getting into a little bit different topic here, but it's sort of, in some ways conceptually, it's related. Just let me make one brief comment about catalysts. A catalyst is something that is going to speed up this process. This is the oxidation of the iron, but in the end, it remains unchanged. Some part of the step, the catalyst, is usually modified in some sense, maybe in just a very minor sense. But if you compare before and after snapshots of the catalyst, it hasn't changed. So that's the basic idea of a catalyst, and I'll get into it more in the last lecture. So I've borrowed just a little figure from the book to help illustrate this reaction rate. A going to B. So yeah, I've used it before. So it's a very simple notion of a chemical reaction. And I don't know if you remember, but at the end of the chapter 4 talk, I mentioned that, in the next chapter we really won't talk about one particular type of chemical reaction. We talk about this kind of conversation about reaction rate can be used for any kind of reaction. That's oftentimes why I fall back to this generic label, A going to B, and then we can dump the mathematics on top of this simple equation. It sort of makes it a little easier to pick out initially, I think. The reaction rate, think of it as the velocity of the reaction, like I mentioned earlier, and it's an exponential rate. We'll appreciate that as we look at some of the graphs for the chapter. But essentially what that means, this is not math class, so we're not going to do a lot with the exponential notion, formula, however you want to say it. But essentially, when you hear exponential, that means there's an extremely rapid change at the beginning, and it slows down as it proceeds toward the end, if you will. And we'll see some graphs that show that. If you just sort of try to squeeze it in over here. If I talk about, let's say the concentration of A, let's say I don't have any room here, but on this we'll say the concentration of A, and then time proceeding out in that direction for the graph. So with a reaction rate, if I'm describing it as exponential, of course there's going to be, you can see here, the red spheres are decreasing over time. After 40 seconds, it's only, 30% of the total amount of molecules or matter that's in the mason jar here. And so what you see with an exponential rate, again, a very rapid drop at the beginning, and then it slows down. And then at some point it levels off, actually. It levels off, and it's not going to change all that much, to tell you the truth. It reaches a state of equilibrium. And so at some point when it levels off, this is actually chapter 15. That's the next chapter that we discuss. I'll point this back out when we come to chapter 15. And then this is what we're curious about. This is chapter 14 for us right now. This exponential decay, this reaction rate. So appreciate, how do we describe this change? Well, it's the concentration is changing over a particular period of time. Well, that seems like a pretty good place to start for me. If I want to talk about the rate with respect to A, well, I can say the change in the concentration of A over the change in time. I mean, that's what I'm describing here with this decrease. And then at some point the change stops. It becomes a zero rate in some sense. It's a constant. It doesn't change anymore. So this is where we begin in terms of the notion of the reaction rate. What are these going to be measured in? Concentration is going to be measured in molarity. Time is usually measured in seconds, but it could be minutes, it could be hours. It depends on how slow or how quick the reaction is. Femtoseconds, that's 10 to the minus 15. Picoseconds, 10 to the minus 12, a trillionth of a second. There's even studies that throw around that unit a bit. Anyway, this is the basic layout. It's going to be molarity change per second is a common unit that we're going to see for the reaction rate. And if I was to plot B here, I'm getting a little wordy on this, but this can be a little bit. I want to go ahead and jump right into the graphs because it's something that we just see over and over and over again. If I talk about in red now, if I talk about the rate of change in it, so again, in red it's going to be B. If I talk about the rate of change in B, well, here initially at 0 time, that's right, that's 0 time there. There's no B. So the concentration is 0, and then over time we see that it increases exponentially, and then again at some point there's no change, and it's at equilibrium. And the same goes here, and we'll do both examples. B, change in concentration of B over time would be the value that we're looking at for this thing. So let's just do a little bit of calculations here for A. Let's just take this, and I want to go from 0 time to 40 seconds. Okay, this is whenever you discuss change in, okay, change in means final minus initial, always. There's no exception to that. Just etch that into your brain. That's going to help you with this particular problem here. So again, if we say the rate with respect to A, I say that, well, it's the change in the concentration of A over the change in time. And so the universal symbol for change is this little triangle, delta. Delta, concentration A, delta T. With this in mind, I say the concentration of A in the final state minus the concentration of A in the initial state. Oops. And I'm using the subscripts here to tell me a story. This rate, I'm talking about A, this concentration is the final, etc. Oops. And actually I just Sorry, I shouldn't have had the delta there. That's it doesn't make any sense. It's just final minus initial. T final minus T initial. And just a heads up, I'm going to modify this in just a minute. I'm trying to make a point in terms of something here. And then at this point we just plug and chug. So one thing to note, this isn't listed here, but it's in the figure. 1 liter. This mason jar is 1 liter. You got 1 mole of A, so that means that if you want to talk about the concentration of A, it's 1 molar here. It's 0.54 molar here, and so on. So they've simplified the model here just to get through the math. We have a problem in that top expression there. Okay, let me just get the bottom one here. This one's okay. 40 minus 0, that's a positive number. 0.3 minus 1, that is a negative value. Okay, let's appreciate that idea for a moment. A negative rate. Well, I mean, the negative value is an indication it's decreasing over time, but when chemists measure the rate of a reaction, we want to make it look like a velocity, like miles per hour. You know, if a car is coming toward you or going away from you, it's still traveling at 60 miles an hour. And so whether you're measuring A, the disappearance of A, or the appearance of B, like I talked about here, we still want the rate here to be a positive value. Okay, so then we need a slight modification in this expression, again with the appreciation of the numerical value that's being dumped out here. If we talk about the disappearance of a reactant, we need to include a negative sign in this expression. Because then, if we complete the story, negative 0.7 molar divided by 40 seconds, and the value now is a positive 0.075 molarity per second, or molar per second. So we're talking about how the concentration changes with time. It's like a miles per hour kind of unit, really. And just a heads up, there's if a unit comes into the subscript, oftentimes you're going to see it as in this form on one line, where s raised to the -1 power is equal to that. So in case you're a little rusty on your notation here, that's s. That's the true statement. So we can easily just substitute either. Like we could use either one of these expressions here. All right. So that's the expression with A, and the problem in the book. What do you know? We're back to this. Now we're dealing with B. Remember B, it starts off 0 and it increases exponentially, and at some point it levels off, and we want the rate of, and I'm going to do this quickly here, same expression. We're curious about the changing concentration per time. Now if we start plugging in the numbers, the final minus initial, well, what do you know? We come up with the same value. Oops. We come up with the same value here. Just appreciate that fact. Again, whether the car is coming toward you or the car is going away from you, it's still going 60 miles an hour. And in the context of a reaction, some simple notion of a reaction, A going to B, whether we talk about the disappearance of A or the appearance of B, we want that same 60 miles per hour. We still want that same value each time. Now, there can arise a few problems here, a few issues, and I'm just going to use an example that's in the book, and it's the dissociation of this hydrogen iodide gas here to its 2 elemental forms. 2 and 2. Yeah, it's all balanced out. Now why? Okay, so if I want the rate of the reaction, again, I can follow the disappearance of that, the appearance of that, or the appearance of that, and it should give me the same value. It has to give me the same value. Okay, whether you have a little moped traveling 30 miles an hour toward you, or a big old 18-wheeler 30 miles an hour toward you, it's still the same rate, whether it's big or small. Okay, and that terrible analogy that I'm trying, what's happening here is that, if we talk about the rate of the disappearance of HI, this is a 2-to-1 ratio between the reactant side and the product side. So there's a stoichiometric there's a stoichiometry that we have to worry about here. This thing disappears twice as fast. So again, the rate needs to be equal whether I'm looking at this guy or that guy. And we know we need a negative value because we're talking about the reactant here. Now remember, this is positive with the product. This is negative for the reactant. And well, actually, let me be a little wordy here. Let me just point out something we know that's true based on our calculation. You don't have to take my word for it now. We did the calculation. We saw that the rate for the overall reaction, whether I'm monitoring A or B, it was the same value, is equal to 0.175 molarity per second. And to do that, we had to factor in the negative value. This is a 1-to-1 stoichiometric ratio, 1A to 1B. That's not the case here. When this reaction goes forward, this thing disappears, twice as fast as either one of these are going to appear. So the short answer is whatever molar coefficient here, you take the fraction and put it in front of that rate expression. And now this will have the same numerical value, whatever it is. I don't have the data for it, so we don't have to calculate it. But there is a stoichiometry involved in these reactions. Okay, now what I've been talking about here is really what's referred to as the average rate, actually. If you especially going A to B from 0 to 40 seconds, it doesn't really tell us the details of the reaction. If this is 40 seconds and this is 0 seconds, the rate of change here was much faster than the rate of change at 40 seconds. And then this calculation is only telling us the average rate of change. If on let's say you have a 30-minute commute on the interstate, sometimes you're going at 80 miles an hour possibly, sometimes you're going at 55 miles an hour. And so over that 30-minute time period, so again 0 to 30 minutes your commute, let's say in this window of time you're going 80 miles per hour, and in this window of time you're going 55 miles per hour, and then through here you're going, let's say, 70 miles per hour. You're all over the place in terms of your velocity of your rate going home. And if you plot these and say, okay, well, from here to here it took so much time, so you had a distance over time here on the full 30 minutes, and you might average out, I don't know, let's say 68 miles per hour. Okay, if the speed limit's 60, you'd say, well, I wasn't speeding. But if you just passed a cop right there, and he or she gets you with the radar gun, and say, my, 80 miles per hour, you got a ticket possibly, depending on how the cops feel, of course. And so there's a difference. there's a difference between the average rate, average velocity, and then this is something called the instantaneous rate or velocity. Reactions have the same way. Let me show you how to pick that out. We don't have a radar gun, so it's not that simple. Here's a reaction that follows us through for a while. I don't care if you understand this. I'm not too worried about it. I just wanted to give you something to look at. This is a reaction in organic chemistry. It's called a hydrolysis reaction. And it's going from, there's the reactant over to the product. And that's what the disappearance of the reactant is being plotted here. We see here concentration of the reactant. And it decreases quickly here, and it slows down here. And then at some point out here, it levels off, and we're in a different chapter at that point. Again, if I said here to here and average and figured out the calculation, I'd get a fairly low average rate. Whereas if I went in at just this one point and figured out the rate of change at that one point, that would be the instantaneous rate. And so that's what we're going to be working on. It's a graphical method that we have to worry about. And the average rate can be, in this particular table that's in your book, they break it down into 50 second intervals in terms of measuring the average rate. And you can see there's a slow decrease in the average rate, molarity per second over time. And this data is just, well, it's a different way to represent the data that you see here. I just took those data points and plotted it out. Then I had Excel actually give me a linear regression, tell me how well it fits with an exponential. Just a little comment here, because you have to do this a few times. Whenever you plot this data, whether it's an exponential value or a linear, a straight line, remember that's y equals mx plus b. I'll talk more about it later. This r squared value is pretty handy. If it's 1 or if r squared is equal to point, at least I like to see at least 3 nines there. Whatever's out here, I don't care. But if you have one of these, it tells you that the data is very good and it's very linear or very exponential. And so this hydrolysis of this terbutyl chloride is the name of this compound, is really a perfect exponential decay, which makes me wonder if they made the data up, actually. I guess it could fit that well, but that's a really perfect example of a reaction rate. And one thing we're going to learn, this refers to the first order reaction. That's the second talk. But right now, I just really want to deal with average versus instantaneous velocity. I am running out of time a little bit here. I do try to keep the lectures to, no more than 40 minutes or so, just because with this, I'm hoping that you're pausing this at a few points and catching up on the notes. That's wouldn't be a bad idea. So I'm anticipating you guys are probably sitting in front of the presentation for longer than maybe up to an hour even. Anyway, the average rate here, all they're doing, right? We had change in concentration over change in NT. This is the rate, and now we know. The equation earlier. That's the average rate, and you can spread it out over a very short period of time or a very long period of time. And again, if you want to talk about how fast am I going at this particular time, you want to try to shrink the interval as small as possible. Well, there's some limitations on this kind of data. We don't have any kind of experimental data between 0 and 50. All we have is this tabulated data and then this graph here. And you can say, well, if I want something, I want to know the rate right at this point. How do I do that? Well, the way we do that is we need to figure out the slope of the tangent at that point. So remember, slope is rise over run. So we're talking about the change in y over the change in x, which corresponds to the 2 units we've been talking about: change in concentration, change in time. Okay, so it's right. You can see it here on the graph. And so notice what they're doing. And what I'd recommend is just when you have one of these plots, just hand draw a tangent line. And one thing you're looking for is, well, it's like the gap up here is about the same as the gap down there. So equal distance out from this point, you're about the same type of gap between the data point and then the line that you've drawn. And there's always some variation in the calculation. You'll see it in the next example that I'm doing. But what it allows you to do is figure out that instantaneous rate. It's like the radar gun that just got you busted for a speeding ticket. It's telling you the instantaneous rate. Actually, I knew an attorney. He was, long story short, he was actually assistant DA for New York City back in, I don't know, 50s, 60s. I guess he retired in the 70s. And yeah, he's a good lawyer. He could argue really well. And he and his wife were traveling out in Arizona and New Mexico, and the cops bust him, with this instantaneous rate is what they got him on. And so he says, well, he wants to debate. He wants to argue the ticket in front of the sitting judge. And so he and his wife go into the, I don't know, probably not clerk of court, the magistrate's office, whoever is in session at the time to hear these little things. And he starts on his argument. He says, well, I traveled from point A to point B, and it took this period of time, and that's around 50 miles an hour. How could I possibly have been going 70? Well, the judge did not understand the notion of average versus instantaneous rate. I'm not even sure if this lawyer friend of mine knew it either, but he got off. He didn't get the ticket. The judge didn't appreciate that. Well, that's only the average rate. If I talk about this long period of time, yeah, it's going to look really slow, but if I measure the change at this point, it's going to be very rapid. And but anyway, he was able to argue his point and get out of the ticket. But anyway, it's just happens to be, I think, a decent analogy for this little talk here. Okay, one more slide. Take a look. This is data from, it's a practice exercise, same data. So what I did is, I plotted out on an Excel. There is I'll talk about it in lab. There's I think it's page 419 if I'm not mistaken in your lab notebook, and it shows you how to do data plotting with Excel. Okay, and in lab I'll be happy to talk about it if you want me to. That's fine. But what I did here is I plotted the data. We have our exponential decay. I zoomed in a little bit. It's different. The time scale here is different than what we saw on that first graph. And it wants to know the instantaneous rate at 300 seconds, and that is a particular data point here. And so, I can't use the data that's just on the table. Like if it's 300 seconds, oops. I can't just go in here and say, oh well, what can I do with? I can't do anything with that in this particular problem. I have to draw a tangent. And then what I've done is I've drawn a long enough tangent here to where it crosses over, or it makes connection with points down here on the x-axis as well as the y-axis, to where I actually know what value I'm looking at. Okay, if I had taken that point there as my x and y, that's a little bit harder for me to tell. I guess I can approximate that value, and then if I drop that down to the x-axis, I could approximate that value. It's not so easy. This is easier. Draw a big line and then see where that line crosses over at an intersection or halfway in an intersection on the grid, and it allows you to figure out the data. So again, oops. Rise over run, y over x. That's going to give us molar over second, which is our goal here. And you just plug and chug. And I'm not going to. You can read off. This is what 0.06, 0.07. That means 0.065, right in the middle. Right. Final minus initial. Oh, and I guess I should carry the units through. Molar, it's 460 seconds minus 200 seconds. That is equal to, and I'll just do the full plug and chug, 1.2 times 10 to the minus 4 molarity per second. Let's just appreciate that number back here. And, you know, it's about the same rate between these two, and you know the time span here is fairly short, and so the value is pretty good. The most important thing is that this order of magnitude for that, I guess, for that particular point is what's important here. If my order of magnitude, oops, you know, if this had been 10 to the minus 9, the answer would have been wrong. If this was on a quiz or a test or something like that. Actually, the answer the book gives is that. Now, this and that in my book do not vary enough to worry me. Again, orders of magnitude change. If that 10 raised to the whatever number, if that number is different than what the answer should be, that's a problem. And I know there's always going to be some variation in the answer depending, because this is an inexact kind of process, really, what I'm showing you here. When you do these problems, just make sure you show me the work so I know where the numbers are coming from. If you don't show me the work, I just can't give you that much partial credit, or even a lot of times I don't give any partial credit. So just be aware of that. Now, in the next one, the next chapters, or the next talk, we'll pull away from the instantaneous and average rate here. This is a good start in terms of appreciation for what reaction rate means, but in the long term, there's some more sophisticated methods to worry about the rate. Things that don't involve this this sort of laborious in terms of trying to get data out of the system. So thanks for your attention, and look over the material before you watch the rest of the videos. Thanks.